Hi, I'm Diljan F. Dumari, a student from Mapua University. I'm here to discuss about universal testing machine and its mechanical characterization. What is universal testing machine? Universal testing machine or UTM is also known as universal tester, materials testing machine or materials test ring. This machine is used to test tensile stress and compressive strength of a material. As the name implies, it can perform several standard tensile and compression tests on materials, components, and structures. It has a components of two main units, loading unit and a control unit. Under the loading unit, we have the load frame. The load frame of a universal testing machine can be made either by the single support or by double support. The load frame consists of a table where the specimen is placed for the compression test. It has also upper crosshead and a lower crosshead. Crossheads, it is divided into two. The upper crosshead is used to clamp one end of the test specimen, while the lower crosshead in the load frame is the movable crosshead whose screws can be loosened for height adjustment and tightened. Both, both the crossheads have a tapered slot at the center. The crosshead have a tapered slot which is a pair of rack jaw that is intended to grip and hold the tensile test specimen. We also have an elevation scale. The relative movement of the lower and upper table is measured by an elevation scale, which is provided along with the load unit. And for the control unit system, we have a power unit. This unit consists of an oil pump that provides a non-pulsating oil flow into the main cylinder of the load. This flow helps in the smooth application of load on the specimen. The oil pump in the hydraulic power unit is run by an electric motor and sump. We also have loading measure unit in the control unit. This unit has a pendulum dynamometer unit that has a small cylinder with a piston which moves with the non-pulsating oil flow. The pendulum is connected to the piston by pivot lever. This pivot lever deflects based on the load applied to the specimen. This deflection is converted to the load pointer and displays as the load on the dial. It has a range load application that can be adjusted by means of a knob in the loading measure unit. It has a range of 0 to 100 kilonewton, 0 to 250 kilonewton, and a 0 to 500 kilonewton, and lastly a 0 to 1000 kilonewton. The accuracy of the measuring unit controls the overall accuracy of the machine. You also have the control devices. The control devices can be electric or hydraulic. The electric control devices make use of switches to move the crosshead and switch on or off the unit. The hydraulic control device consists of two valves. We have the right control valve and left control valve, or also known as the release valve. The right control valve is used to apply the load on the specimen, while the left control valve is used to release the load application. We have two main types of universal testing machine. These are based on performance, mainly mechanical or hydraulic universal testing machine. For the mechanical, electromechanical machine uses an electric motor, gear reduction system, and one, two, or four screws to move the crosshead up or down. Its range of crosshead speeds is achievable by changing the speed of the motor. A microprocessor-based closed-loop servo system can be implemented to actually accurately control the speed of the crosshead. While for the hydraulic, in this type of machine, either uses a single or dual acting piston to move the crosshead up or down. In manually operated machine, the operator adjusts a needle valve to control the rate of loading, which in a closed-loop hydraulic servo system, the needle valve is replaced by an electrically operated servo valve for process control. Generally, the difference between these two types is this. An electromechanical machine is capable of a wide range of test speeds and long head crosshead displacement, whereas for the hydraulic machine, it is a cost-effective solution for generating high forces. The simple procedure of this machine or the universal testing machine, whereas the specimen is placed in the machine between the clips, and an extensometer, if required, can automatically record the change in the gauge length during the test. If an extensometer is not fitted, the machine itself can record the displacement between its crossheads on which the specimen is held. However, this method not only records the change in depth of the specimen, but also other extending or elastic components of the testing machine and its drive system, including any slipping of the specimen in the wheels. Once the machine is started, it begins to apply an increasing load on the specimen, while throughout the test, the test control system and its associated software record the load and the extension or compression of the specimen. The test produces a curve mainly known as the stress-strain curve. For a material, this gives the relationship between the stress and strain. It is obtained by gradually applying the load to a test coupon and measuring the deformation from which the stress and strain can be. That is an example of a stress-strain curve, where it shows an engineering stress or extreme stress and an engineering stress or extrusion stress. Now, for the preparation of the test specimen can take either round bar, rectangular bar, or sheet physical structure of the test. A 2-inch gauge length is marked on specimen carrier for testing. The specimen is held in the clamps at either end while the load and the movement are applied to the clamp. The UTM, or the Universal Testing Machine, has a functions that can test several mechanical properties such as tensile, compressive, torsion, or shear and bending. For the tensile test, the elongation during testing is measured with respect to the gauge length using an extensometer. As the specimen elongates, the extensometer reading is recorded either real-time or at a discrete time intervals. Extensometer can either be analog or digital prior to the test. As you can see on the left side, this is a diagram or uh, elastic stress or strain curve, which explains the necking or the fracture of a sample specimen. For the compression test, compressive, compressive stress is a force that causes a material to deform to occupy a smaller volume. When a material experiencing a compressive stress, it is said to be under compression. A high amount of compressive stress, such as tensile stress, leads to failure due to compression. At the left side shows a compression test wherein the the specimen is compressed to its deformation and then showing the diagram or the curve of the deformation where we have compressive load versus the plastic deformation or the strain. Third, we have torsion test. Torsion testing is a type of mechanical testing that evaluates the properties of material or device while under stress from angular displacement. Torsion testing can be split into two distinct categories. First is testing raw materials like metal wires or plastic tubing to determine properties such as shear, strength, and modulus. Or functional testing of finished products subjected to torsion such as screws, pharmaceutical bottles, and sheeted cables. The most common mechanical properties measured by torsion testing are: one is modulus of elasticity and shear, yield shear strength, ultimate shear strength, modulus of rupture and shear, and elasticity of fluid. On the left side, as you can see, is a graph of the torque versus the rotation angle happened or occurring on the tensile specimen. Fourth, we have a shear stress. A shear test is designed to apply stress to a test sample so that it experiences a sliding failure along a plane that is parallel to the forces applied. Generally, shear forces cause one surface of a material to move in one direction and the other surface to move in the opposite direction so that the material is stressed in a sliding motion. Shear stress in a sliding motion differ from tension and compression tests in that the forces applied are parallel to the two contact surfaces, whereas in tension and compression, they are perpendicular to the contact surfaces. Double shear test is usually made in the universal testing machine. And as you can see on the left, we have a single shear stress testing or double shear testing. The figure below shows a double shear testing made in the universal testing machine. And lastly, we have the bending test. Bending test, sometimes called flexure testing or transverse beam testing, measures the behavior of materials subjected to a simple beam loading. It is commonly performed on relatively flexible materials such as polymers, wood, and composites. At its most basic level, a bend test is performed by placing a specimen on two support anvils, which is bent through applied force on one or two moved anvils. The force is applied with either a single upper anvil at the midpoint, which is a 3-point bending test, or two support anvils equidistant from the center, or also known as the 4-point bending test. In a 3-point test, the area of the uniform stress is quite small and concentrated under the center loading point, while in a 4-point test, the area of the uniform stress exists between the inner span loading point, typically half the length of the outer span. So mainly, bending tests can be done through 3-point and or 4-point bending test. At the left side, as you can see, is a diagram of a 3-point, and on the letter B, we have a 4-point bending test. Below shows a graph of a 3-point flexural stress versus strain. And that's it for today or for this video. Thank you for listening. And that's the universal testing machine